So in the third approach, let's try to use union find method in graph theory. Let's remember in the approach 2, we use the definition for a tree. The definition is to simplify the problem down to checking whether or not the graph is fully connected. If it is fully connected and if it contains n-1 edges, then we know it is a tree. And in the previous approaches, we used a graph searching algorithm to checking whether or not all nodes are reachable starting from a single source node. So another way we could approach this problem is by considering each connected component to be a set of nodes. When the edge is put between two separate connected components, they are merged into a single connected component. And we will use the example, let's say when n is 6, we have 6 nodes. And we have the edges 0 and 5, 4 and 0, 1 and 2, 4 and 5, 3 and 2. So before we look at the edges, we have 6 sets. Now we can then go through the list of edges and merge the sets together. For example, because the first edge is 0, 5, so we merge the sets with 0 and 5, and this means that we now have 5 connected components, and 0 and 5 are merged into a single set, which leaving 5 sets. The next edge is 4 and 0, therefore we just merge the sets 0, 5, and 4. And then we should remember that because 0 and 5 are connected and 4 and 0 are connected, this means that 4 and 5 must be also connected, and 0, 5, and 4 are merged into a single set, so we're leaving 4 sets now. So we can continue the same process until we are gone through the edges. The conclusion we can draw from this example is that these edges are not in a single connected components, and therefore they must contain a cycle. So the algorithm should return false. And here is another example where the edges do form a single connected component. And we should notice that in the second example, every edge resulted in a merge operation. But in the first example, some of the edge doesn't result in a merge operation, right? This was because there was some cycles in the graph. Each time there was no merge, it was because we were adding an edge between the two nodes that we were already connected via a path. This means that there is now an additional path between them, which is the definition of a cycle. Therefore, as soon as this happened, we can terminate an algorithm and return false. Now, how should we implement this? Well, we could create a list of sets and then carry out the algorithm as it was done. However, there is a better way. It is a really clever algorithm which we call union find. I will give a brief introduction to the algorithm here. Union find is a very useful algorithm that can be used to solve many graph problems. Union find represents each of the sets as a directed tree with the edges pointing toward the root node. For example, consider the graph from our first example above, the one that is not valid tree now. So one way is connected components could be represented a union find is like this. Union find is a data structure with 3 methods: make set A, find A, and union A and B. The make set A method is the simplest. It just creates a new size 1 set containing just element A, and the find A method starts at A and it traces parent link up until it gets to the A's tree root. It then returns the tree root ID. So if there are 2 nodes are in the same connected components, then they must have the same root. And if they are in a different connected components, then they will have different root. And for the above example, we use find 0, find 4, and find 5, and it will all return 5 as our root node, and whereas we use find 1, find 2, and find 3, and it will all return 1 as our root nodes. So this method can be used to check whether or not two elements are in the same connected components, and it also can be used for the union A and B method, as we are going about to see them. The union A and B method works by finding the root for A and the root for B by using the find operation. It then sets B's parent to be A, thus combining the two trees into one. For example, if we add 8, 4, and 3 to the example above, the algorithm will find that the root of 4 is 5 and the root of 3 is 1, and merge these subtrees. Once this is done, all of the nodes have the same root of 5, and therefore we know that they all belong to the same connected component. Actually, we don't need to use linked node to represent this structure. We can just simply maintain an array of parent pointers. For example, here's how the above tree is represented as an array, which is the parent pointers array. And we should notice how 5 simply points to itself as it's the root, and the find operation works its way up parent link until it finds the node that points back to itself. So if we want to get a valid tree, it should meet these 3 conditions. The first condition is it should have n-1 edges, and the second condition is it should form one single connected component, and the third condition is there must no cycle in these connected components. So only meet these 3 conditions can form a valid tree, which will return true. So now let's say we have edges 0, 5, 4, 0, 1, 2, 4, 5, and 3, 2. And now let's create a parent array, which is 0, 1, 2, 3, 4, 5, and then it have index, which is also 0, 1, 2, 3, 4, 5. So this represents we initializing all set, and its nodes, every node have its parent is themselves. So now let's try to use a for loop for A, B in edges. So it will check the first sublist 0 and 5. We try to use self.find to find 0's root is 0 and 5's root is 5. So root of A is not equal to root of B. So we try to merge them together by assign root of B into the parent of root of A, which is change the 0 into 5 in the parent array, and then we return true. Now let's try to check the second sublist 4 and 0. 4's root is also 4, but 0's root is become 5 now, and we try to merge them together. We just try to change the 4's parent into 5 and return true. So now let's look at the third sublist. We have 1 and 2. 1's root is 1 and 2's root is 2. So to merge them, we just change 1's parent into 2 and return true. So now let's look at the fourth sublist. It has 4 and 5. 4's root is 5 and 5's root is also 5. That is, the root of A is equal to root of B. So that means A and B is already in the same set. It will form a cycle. So we just return false to represent it is not a valid tree. If we try to represent this algorithm into linked node representation, it will be like this. First, we connect 0 and 5, then we connect 0 and 4, and then we connected 1 and 2, and then we connected 5 and 4, and it will form a cycle. So we directly return false to represent it is not a valid tree. We need to check whether it is a valid tree. So first, we have example here, n is 6 and we have 5 edges. And then first we should create a class solution. So in this class solution, we should define a valid tree method which have self and n, which is integer, represent how many nodes we have, and edges, which is the 2D list, and it contains another list, and inside this 1D list it have a 2 integer, which means which two nodes connected with each other, and then it will return Boolean value to tell us whether or not it is a valid tree. So before we continue next step, we should go back to the beginning and from typing import list so that we can use the list, right? And then let's go back to the valid tree function. So now let's judge the edge case. if the length of the edges is not equal to n minus 1, we should return false. So they have two edge cases. The first case, if length of the edges is greater than n minus 1, then that means we have more edges than nodes. That means some of the nodes are from a cycle, so that it should return false. And the second edge case, if length of the edges is less than n minus 1, that means some of the nodes without a connection with the edges or paths, so it is not fully connected, we should return false. So in the second condition, we should consider this graph must contain a single connected component. So we just create a new union-find object with n nodes, and then we go back to the beginning and define class union-find, and then we initialize all of the set at the same time in this constructor, which is define double_initialize self at n, and then we build an array which is self.parent, represent the nodes the parent, and we create this array by node for node in the range n. So it will generate an array from 0 to 5, and the index is also 0, 1, 2, 3, 4, 5, represent the nodes the parent. So here we use a for loop for AB in edges. We just add each edges alternatively AB, AB, AB into the union find dot union. So if it is not union find union AB, so then that means the merge didn't happen. In that case, we return false. That means it must contain a cycle. So now let's go back to union find class, and we try to define the method union, which have two arguments, a and b, and we try to find the roots for a and b, which let's named root underscore a, which we use the find method to find the root of a, and the root underscore b is assigned by self.find b. We try to use find method to find the root for node b. Let's go back to the union find class, and we try to define find method which have self and a argument, and we use a while loop until it finds the root node. It will keep running the while loop. So the condition is a is not equal to parent at a. So what it means a is equal to parent at a, that means we find the root node. So if we don't find the root node, we should update a assigned by the parent at a, so it will keep traces up the parent link. So until we find the root node, and then we just return a, because a is updated to the root node. We just return a so we can get the root node. So now let's go back to the union method. Let's finish them. So first we should check the edge case. If a and b already in the same set, that means the root of a is equal to root of b. We directly return false, because a and b have the same root. They are already connected, and if we merge them again, they will have another path, so it will form a cycle. So we just directly return false to tell them it is not a valid tree. And if the root of a is not equal to root of b, at that time we can merge them. We can merge the sets contain a and b. We just assign root of b into the parent at the root of a. And then after finished merging, we should return true to tell them its merge is happened, and we return true. Now let's go back to the class solution valid tree method, and we return true if it passed all of the tests. And then let's print out the result, print solution, which will return false because it contains a cycle. Let's analyze the complexity. We let E be the number of edges, and let N be the number of nodes. And when E is not equal to n minus 1, we just simply return false. So therefore, the worst case is when E is equal to n minus 1. And because E is proportional to n, so we will say E is n to simplify the analysis. We are putting each of n edges into the union find data structure. So by using union method, the union method itself has no loops or recursion. So the entire cost of calling it dependent on the cost of the find method, that is cost. The find method's cost is dependent on how far the node it was searching for is from the root. So by using the naive implementation of union find, the depth could be n. So If this was the case for all of the costs, we would have a final cost of O of n squared time.